welcome to the next episode of electromagnetism. Today we're diving into the craziest theory in all of modern physics, the idea that there are no magnetic monopoles. Let's dive into Maxwell's second equation. This is the equation we're going to be trying to understand today. The divergence of the magnetic field is equal to 0. This equation might look small, but it is mighty. Today we're going to break down what each of these symbols mean, from this upside down triangle to this dot to this B to this arrow, and even to why there's a 0 on the other side. But before we dive into Maxwell's second equation, let me quickly review what we did last time with Maxwell's first equation, the divergence of the electric field. So last time we looked at the divergence of not the magnetic field, but the electric field, which is proportional to the total charge density inside some region. So I used two analogies to help explain what this really means. Let's say you have a box, and inside the box there are some huge number of balls, but you don't know how many balls there are, and you don't want to open up the box and individually count each one of them. That would be a waste of your time. All you know is that each one of these balls has a certain mass. In fact, they each weigh 1 gram. And when you put this box on the weight machine reads a certain number. It says 100 grams. Well, okay, then you immediately know how many balls there are in your box. You don't have to open up the box and count how many balls there are. You can just say, okay, if each ball is 1 gram and the total box weighs 100 grams, well, there must be 100 balls inside the box. That's all that Gauss's law is saying. It's saying, okay, if I can just count up how many electric field lines are piercing through, popping out of a certain surface, I don't have to open up the surface and count how many charges there are inside. I can just sit back and conclude that there are some number of charges inside. So here's a quick recap. If I have, for example, a plus charge that has electric field lines radially outwards, and I have a circular surface, something like this, then I don't have to open up the surface and say, okay, how many positive, how many negative charges do I have? All I have to do is, even if the surface is opaque, right? Even if I don't know what's inside the surface, I can just say, okay, you have electric field lines that are going out. So that means there's a net positive charge inside your surface. If instead we had electric field lines that were going in, I have a circle, and you don't know how many charges there are or what the net charge inside is, but all I tell you is, okay, here are the field lines for whatever is inside this surface or inside this box. Well, you don't have to open up the surface. You can immediately tell me there has to be a net negative charge inside this box, inside this surface. Why? Well, because if there wasn't a net negative charge, then the electric field lines will be going out. If instead there was a net negative charge, the electric field lines would be going in, as they are in this case. So that's exactly analogous to this metaphor we were talking about here, where you don't have to open up the box and individually count how many balls there are. All you have to do is put the box in a weight machine, and based on what the weight machine reads, you can immediately tell how many balls are in the box. Based on how many electric field lines are going out or in, you can immediately tell the net charge inside your surface. We also talked about a second analogy where we said, let's say you're in a movie theater and for some reason you can't watch the movie. Maybe it's too expensive, maybe you just don't have the money. For whatever reason, you can't watch the movie. But you give yourself a second best deal, which is you try to figure out, is the movie any good? Okay? Unlike most people, you don't go to RottenTomatoes.com. Instead, you think of a brilliant idea. You stand outside of the movie hall and you look at how many people are going into the movie theater and how many people are going out. Because if the movie is really bad, people are going to be walking out of the theater, right? And if it's really good, everyone's going to be staying inside and watching the movie. So what you do is count how many people go in the movie theater and how many people go out of the movie theater. And then you subtract them. You say inside minus outside. How many people go in? How many people went out? That should be, the difference should be how many people are left inside watching the movie. Well, that's the exact same idea behind Gauss's law. You count how many electric field lines are going out and how many field lines are going in. You subtract them and you get the net charge inside your surface. That's all that Gauss's law is saying. So these two analogies should help you understand what Gauss's law is really saying. But before, on a smart board, I couldn't really show you a visual way to understand Gauss's law. But today is different. We have a smart board, and today I'm going to show you Gauss's law in real life. So first and foremost, let me show you the field lines for a negative and a positive charge. So here is a positive charge right here, right? Pretty simple, pretty standard. As you know, the electric field lines for positive charge are simply radially outwards in every direction. Now, what is Gauss's law saying? It's just saying, okay, give me a circle around this charge, okay? And you're gonna see that each one of these field lines pierces the circle as it goes out. So it's almost like these field lines are little pins popping a bubble as they go out of the surface. So this would have a positive divergence, right? So the divergence of the electric field would be positive here. Okay, now let's bring in a negative charge. If I have a negative charge, you have the exact same scenario, but now it's a little different. It's a little different. Why? Well, now look at what the field lines do. Instead of going out, they go in. They go into the charge. And this time, if I put a circle around the charge, yes, again, the field lines, the electric field lines pop the circle, but this time they're going in instead of out. So we would say that the electric field has a divergence that is negative. That is negative in this case. And finally, what if you have a positive and a negative charge? Well, this is what you'd have. This is known as an electric dipole. Okay, now look at what the electric field lines do over here. The electric field lines go out of the positive charge and into the negative charge. So let me draw that again nicely. Out of the positive charge into the negative charge. And so this is what you have. Now, if I create a circle here, what's going to happen? Net divergence is 0. And that should make sense because the net charge inside the surface is also 0. So that's the idea behind Gauss's law. Here is another simulation that gives the basic idea. You can see that each one of these arrows shows the flux out of this box. And even if this box was shaded, if this box was opaque and you couldn't see inside it, you could still guess that the net charge inside has to be positive because the electric field lines are popping out. Take a look at Maxwell's second equation. The divergence of the magnetic field is 0. Let's break down what each one of these symbols mean. All right, folks, so let's break down this equation. What does every symbol here represent? First, let's start with B. What is B? B is the symbol we use for the magnetic field. For electric fields, we used E. Magnetic fields, we use B. Why? That's just nomenclature, but that is what B means. B right here is magnetic field. So that was not too bad. That's easy enough. What about this little arrow on top of the B? What does that represent? That represents the fact that B is a vector field. What does that mean? That means that the magnetic field has two things. It has a magnitude and it has a direction. Right? After all, that's the definition of a vector. It has a magnitude and a direction. That's why you have a little vector symbol here, a little arrow that represents the fact that B is a vector field. It's a magnetic field with a magnitude and a direction. So that's what this arrow right here represents, that B is a vector field. Now, you might not really understand what I mean by that. Yes, I'm saying it's a vector field, it has a magnitude, it has a direction, but what does that mean? What do I physically see? Well, let's take a look at the magnetic field for a basic situation. This right here is a current carrying wire. It's the simple magnetostatic situation you can have, meaning that the magnetic field doesn't change. So in this situation, what we have is this yellow current carrying wire. Let me draw it here as well. You have a current carrying wire. Here is my wire, and let's say the current is going up, right? So the current is going up, and using the right hand rule, curling my hands around and pointing my thumb in the direction of the current, I can figure out that the magnetic field must be going in this direction. and I'm not good with directions. This might be clockwise, counterclockwise, who cares? But the magnetic field has a direction. Okay, how do I know that? Well, if I reverse the direction of the current, you can see that all the magnetic field vectors change, right? Let me do that again. Watch closely as I reverse the direction of the current. Right now the current is going down and the magnetic field vectors are going the opposite direction. Now let's reverse the direction of the current, and you just saw the magnetic field vectors change, right? You can see the current changing here as well. So that's proof. That demonstrates that the magnetic field has a direction. But how do we know it has a magnitude? Well, take a look at what happens when I increase the current. If I increase the current flowing through the wire, you expect the magnetic field to increase, right? Well, let's see that in action. If I have almost no current, you can see that there's no magnetic field. But as I slowly increase the current, observe as the magnitude of the magnetic field increases, right? So this demonstrates the fact that the magnetic field has both a magnitude and a direction. Hence, it must be a vector field. That's why we put this little arrow on top of the B. Okay, so now let's break down the other symbols right here. We also have this little dot, this upside down triangle, and this zeros got a lot of explaining. So let's start with the upside down triangle and the dot. What do they represent? So this upside down triangle, we saw it in the previous lecture as well for Gauss's law for electric fields, but let me break it down once more. So this upside down triangle has a name, and it is called Nabla. This is called the Nabla operator. Okay, and it's very similar in practice to its cousin, the right side up triangle. That is delta, right? Now most people, if you tell them, okay, what does delta x mean? And then they'll say, okay, x2 minus x1. Well, Nabla works almost the same way. If I apply Nabla to something, let's say a function, Nabla you can apply not just to a variable but to a function, then what I'm really saying, what I'm really asking is how much is this function changing in the x, y, and z directions, okay? So Nabla again is like a superpowered version of delta. It tells me how much a function changes in the x, y, and z directions, okay? So mathematically what it looks like is delta f, delta x, delta f, delta y, delta f, delta z. And if you're fancy, you can use derivatives or whatever, but that's the big idea. Nabla just tells you how much a function changes in the x, y, and z directions, okay? Now, there's different ways you can mix and match this Nabla, this upside down triangle, with a function, okay? And let me show you the 3 different ways. You can either, so let's say here's your Nabla, you can straight up apply Nabla to a function. I'm going to call my function B for the magnetic field. If I do that, there's no harm in that. Now that it has to be a scalar function, sorry. So I can straight up apply the Nabla operator to a function, and that would tell me how much the function changes in the x, the y, and the z directions. Now if I straight up apply the Nabla operator to some kind of a function, all that tells me is how much that function changes in the x, y, and z directions. Okay, that's all it's saying. Nothing fancy. That's all it's saying. Now, what if I apply the Nabla operator to a function, but you see a little dot here? Well, what that means is that this dot right here is a dot product. Okay, I'm taking the dot product of the Nabla operator with the magnetic field. Okay, so let's calm down for 1 second and let's try to break this apart. I know that if I apply the Nabla operator to some function, it tells me how much the function changes in the x, y, and z directions, right? Okay, well, let me give you an example. Let's say you have a function like this, okay? Here, x, y, z directions. Let's say I have something like this, a 3D function. So what Nabla B does is it tells me, okay, if I take a certain step, how much does the function change in the x, y, and z directions with every tiny step. Okay, so that's really what Nabla B is telling me. It's just telling me how much the function changes in every direction. Okay, now if I apply Nabla to a vector field with a vector function with a dot product, what does that tell me? Well, amazingly, what it tells me is something that has a real physical intuition. This tells me the flux, or you might also hear it being called the divergence. The dot product of the Nabla operator with the magnetic field tells you the divergence, the flux of that field outside a certain surface. What does that mean? What that means is how much is your field spreading out over a certain region of space. So if I have, for example, this circle and I draw some arrows poking out of the circle, this we would say is an example of positive divergence. On the other hand, if I have the same thing but the arrows are pointing into the circle, this would be an example of negative divergence. If I have the circle but there are more field lines that are pointing out than in, then take the net divergence and it would be positive, right? 3 field lines pointing out and 1 field line pointing in, that means there are net 2 going out. So that's a positive divergence. And if I have the same number of field lines that are going out and in, that means I have 0 divergence. There's a total of nothing changing, right? There's the same number coming in as going out. So that's the idea. So that is what every symbol here means, okay? This right here, this upside down triangle, that's the Nabla operator. Let me draw that with some space. Nabla operator. This right here is the dot product of the Nabla operator with the magnetic field. So this is the dot, okay? And so that's what you have here. So the dot product of the Nabla operator with the magnetic field, this combination is called the divergence. When you see these two guys together, the Nabla operator with the dot product, that means you're taking the divergence of some vector field. Okay, now finally that we understand what every symbol here means, this is Nabla, here's the dot product, together they're the divergence of the magnetic field, which is a vector field. Why is that 0? Well, here is why the magnetic field has a divergence of 0 and why that means you can't have magnetic monopoles. So let's take a look at the magnetic field of a bar magnet. So here is a bar magnet and here are the field lines for a bar magnet, right? So they come out of the North Pole, go into the South Pole, out of the North Pole, into the South Pole. So here's the direction of the magnetic field lines. So they're coming out over here and going in right here to the South Pole. So what is the second Maxwell equation really saying? It's telling us, again, we create a circle. No matter where we put our circle, how big our circle is, you'll observe the same thing. So let's start with a circle right here, a small circle. You'll see, let's zoom into this circle. What do you see? You see that this field line is coming in right here. It's crossing the circle right here. That's too big. So this field line is crossing the circle right here. So when you're coming in, remember, when something is piercing the surface but it's coming in, that means you have a negative divergence. This field line is coming in when this magnetic field line is coming in, piercing in, that's a negative divergence right there. But the divergence of the magnetic field is 0, you said. Well, let's keep going. Keep following. This field line pierces out. And when you have a field line that is piercing out, when it's popping out through a surface, then you have a positive divergence. We immediately can say that this field line that is popping out, piercing through and going out of our circle has a positive divergence. Well, negative and positive, that means you have a 0 divergence in total. So a 0 divergence for this circle. Well, okay, you say, you get defiant, you say, what if we have a bigger circle? All right, well, same idea. You can see here this magnetic field pops in, negative divergence, but the same field line has to pop back out, positive divergence, resulting in a zero net divergence, right? Or zero flux, either way you want to say it. And you might say, okay, wait, but why does this have to happen? Well, look at the big idea. Look at the big picture right here. The big picture here is that every field line that comes out of the North Pole has to go right back into the South. That didn't happen with electric fields. In an electric field, you could have a plus charge where the field lines literally just escaped the charge. They didn't come back. You didn't see that the field line for a plus charge went back into the plus charge. That would be weird. But that's exactly what happens with a bar magnet. Every field line that comes out of north has to go right back into the south. And in fact, what if you have a really crazy field line? What if you have a field line that looks like this? What if you have a field line that's popping out almost like it's going to escape, almost like it has enough escape velocity to go out, to escape the bar magnet? But no, it has to come right back down and meet the South Pole right here. So no matter how far out you go, every magnetic field line has to go right at every magnetic field line that escapes the north has to go right back into the south. And as a result, the total divergence of the magnetic field is zero. But let's say you're getting crazy. Now you really want to prove this thing wrong. So here's what you do. You take a knife and you chop up this bar magnet. You slice it. You slice this bar magnet in the hopes that you can separate the north magnetic field lines from the south magnetic field lines. But what happens? Well, what happens is when you slice a bar magnet, but now there's going to be a south here and a north here. So you didn't really chop off the magnet. You created two magnets now. And so again, the field lines are going to go from north to south, north to south. So no matter how you cut it, no matter how you slice, dice, chop, cut this bar magnet apart, you're always going to have a north and a south pole. You can't have a separate north pole or separate south pole. Nobody's figured out how to do that yet. But a lot of physicists are searching because it seems like there's got to be magnetic monopoles out there somewhere. But we just can't figure out how to make them. No matter how you slice or dice a bar magnet, you're always going to have a north with a south. You can't separate the north into its own magnetic charge like you can do with a positive or negative electric charge. No, these guys, they're like peanut butter and jelly. They have to come as a pair. And as a result, the divergence of the magnetic field always has to be zero. So ladies and gentlemen, that concludes our episode on Maxwell's Equations number 2. We'll see you in the next one.